For years, Boeing has been caught in a downward spiral, losing billions of dollars since 2019 and fighting an almost non-stop series of setbacks that have shaken public confidence. Every new headline seems to remind the world that one of the most iconic aerospace companies on Earth is struggling to keep its aircraft reliable, safe, and in the air. While Boeing battles defect after defect and delays pile up across its production lines, something completely unexpected has been happening on the other side of the tech world. Elon Musk, who already transformed electric cars, solar energy, rockets, and AI, has quietly been building something that could disrupt yet another industry. In 2026, Tesla's super electric plane emerged as a fully designed, shockingly capable aircraft, marking a moment that could signal the beginning of an entirely new era in aviation. The real shocker came when Musk hinted that Tesla could eventually manufacture up to 10,000 electric aircraft. Not prototypes, not concepts. Real, mass-produced electric jets ready to fly. For comparison, Boeing typically produces around 400 to 600 planes per year during its strongest years. Musk's announcement wasn't just confidence, it was a declaration that Tesla sees a future where electric aviation dominates, and legacy aerospace companies may no longer lead the sky. Observers wondered what gave Musk the confidence to step straight into an industry that has resisted radical change for nearly a century. The answer lies in Tesla's technological breakthroughs, many of which have been dismissed, doubted, or mocked until they became reality. The idea of a long-range electric aircraft has been considered impossible for decades. Engineers have repeatedly emphasized that batteries are too heavy, energy density is too low, charging is too slow, and regulations are too strict for electric aviation to scale. But the 2026 Tesla super electric plane challenges every one of those arguments at once. Musk's aircraft is a supersonic EVTOL, vertical takeoff and landing jet capable of reaching extraordinary speeds, operating without runways and achieving ranges that experts claimed were physically impossible. What turns this concept into a shockwave across engineering circles is Tesla's achievement of a 1,500-mile flight range using a compact airframe with wings so small that aerodynamic traditionalists were baffled. The fact that Tesla managed to create a sleek aircraft that appears too small to fly far, yet reaches cross-continental distances has forced analysts to reconsider what they thought they knew about physics, battery systems, and electric propulsion. Musk has spent more than a decade hinting at an electric jet, but the timing was never right. He once said that Tesla needed at least 400 watt-hours per kilogram. Battery packs before an electric jet would be realistic. By 2026, Tesla not only crossed that threshold, they went far beyond it with new, aluminum-based and silicon-enhanced cell chemistry. This allowed Tesla to create batteries light enough, strong enough, and energy-dense enough to power a supersonic EVTOL for hours, while Boeing continues dealing with financial losses, production halts, federal investigations, and repeated safety issues. Tesla has been refining manufacturing techniques, reinventing materials, and optimizing AI-driven aerodynamics. Boeing's issues have created a vacuum that Tesla is now positioned to fill. Musk's courage to enter aviation did not appear out of nowhere. It is rooted in a decade of battery innovation, breakthroughs in electric propulsion, mastery of automation, and a proven ability to scale technology that experts once believed was unscalable. The same people who doubted Tesla's ability to mass-produce EVs, build billion-dollar gigafactories, or launch reusable rockets are now confronting a new reality. Tesla may truly be capable of reinventing flight in a way no modern aerospace company has attempted. The 2026 Tesla Super electric plane is the result of solving dozens of engineering challenges that aerospace firms have struggled with for years. The first major breakthrough is the propulsion system. Instead of relying on traditional jet engines, Tesla's aircraft uses electric ducted fans powered by high-density battery packs. These fans generate instant torque, quiet thrust, and efficient power usage, allowing vertical takeoff and landing without the deafening roar of typical jets. By integrating Tesla's next-generation motors, which spin at extremely high RPM with minimal heat lost, the aircraft delivers incredible acceleration and lift, all with significantly lower maintenance costs than fuel-based engines. The second breakthrough is what analysts are calling Tesla's smart wing. These compact wings are far smaller than what is typically seen on long-range aircraft, yet they outperform expectations due to adaptive geometry. The wings are equipped with dynamic surfaces that shift shape mid-flight, responding to air pressure, turbulence, and speed in real time. Combined with advanced CFD modeling, these wings allow the aircraft to slice through air at supersonic speeds while maintaining stability and minimizing drag. It's a complete reimagining of how wings work, more like a living aerodynamic system than a static aircraft part. Then comes the battery architecture. Tesla didn't simply install a large battery pack into a jet. They redesigned the aircraft around the battery, using a structural battery concept similar to what was introduced in the Tesla Model Y, but scaled to aviation. The entire fuselage becomes part of the battery system, distributing weight evenly and reducing structural mass. This allows the plane to carry more usable energy without feeling heavy or sluggish. The aluminum-ion and silicon-enhanced chemistry drastically cuts weight while delivering more energy per kilogram than anything Boeing or Airbus have tested publicly. Charging such a massive system might seem problematic, but Tesla engineered a solution for that as well. The aircraft can recharge using a specialized high-voltage supercharger platform, capable of filling the battery in under 25 minutes, far faster than any current commercial aviation fueling schedule. For longer turnaround needs, Tesla designed modular battery docking stations that allow a depleted pack to be swapped out entirely, making the aircraft ready for flight with almost no downtime. This innovation alone could transform regional air travel by making electric aircraft commercially practical. Another enormous hurdle was FAA approval. Electric VTOLs have struggled to get certification due to strict requirements. But Tesla adopted a radically different strategy. Instead of designing a futuristic aircraft and then trying to get regulators on board, Tesla designed the aircraft from the beginning with FAA constraints built into the blueprint. Every component, fuselage materials, safety systems, redundancy circuits, avionics frameworks, was crafted with regulatory approval in mind. This is why Tesla managed to pass through some of the harshest FAA qualification stages in record time. They learned from SpaceX, from Tesla Automotive, and from years of navigating regulation-heavy industries. That experience became one of their biggest advantages. When people first heard that Tesla achieved a 1,500-mile range on a VTOL jet, they assumed it was either hype or impossible. But the combination of battery breakthroughs, aerodynamic optimization, lightweight materials, and propulsion efficiency makes it achievable. The aircraft's small wings are not a disadvantage, they are part of a completely new design philosophy. Traditional aircraft rely on large wings for long-range lift because they burn fuel, which lightens the aircraft over time. Electric aircraft do not burn off weight. So Tesla engineered a system that continuously manages airflow, minimizing energy waste. The result is an aircraft that maintains efficiency throughout the entire journey. This range doesn't just disrupt private jets. It threatens to redefine commercial aviation models. Small airports could become hubs for quiet, clean, long-range EVTOLs. Traveling from Los Angeles to Chicago, or from London to Rome, or from Dubai to Mumbai could soon be done without fuel, without huge runways, without the noise pollution associated with conventional aircraft. Tesla's range also enables unique operational advantages. Aircraft can fly city to city without the infrastructure overhaul that typical jets require. Urban vertiports, islands, remote areas, regions with limited aviation support suddenly become accessible. Another advantage Tesla holds is manufacturing scale. Boeing is struggling to meet production schedules even for existing aircraft. With supply chain breakdowns and quality control failures across multiple facilities, Tesla, by contrast, has mastered high-volume production using gigafactories, robotics, and machine learning optimization systems. Building 10,000 electric aircraft becomes more believable when considering Tesla's record of producing millions of vehicles per year, each one using advanced materials, complex electronics, and massive battery packs. Elon Musk has repeatedly said that manufacturing is the hardest and most valuable part of engineering. And Tesla's factories prove that statement every day. Boeing still relies heavily on manual labor, subcontractors, and outdated processes. Tesla's automated production ecosystems could complete fuselage segments, wings, and propulsion systems with far more consistency and speed. With all these elements combined, it becomes clear why Musk was confident enough to push Tesla into aviation now rather than waiting another decade. The technological foundation was finally ready. The market gap was wide open. Public frustration with traditional aviation is growing, and environmental pressure is stronger than ever. Meanwhile, Boeing's brand has been damaged by ongoing failures, grounding events,